What's going on, everybody? Mr. Dickin here. In this video, we are going to be finding zeros of polynomial functions using the polynomial factor theorem. So when we're going through and doing this, we are going to rely pretty heavily on synthetic division to get the work done. Now, when we're finding zeros of a polynomial, I'm just going to make up a graph here. Let's say we had, a cubic function. So a cubic function might look something like that. Okay, so right now I'm noticing that this graph, it looks like it's got, let's see, 1, 2, 3 zeros, right? 3 x-intercepts. And if I graphed that, it would be pretty easy for me to determine that. But what if I had a scenario in which, I have my graph and the cubic maybe looks something like this? Well, now I've only got 1 x-intercept, but I know that there has to be 3 solutions, so the other 2 are manifesting as imaginary roots. There's no way for me to find that on the graph. They don't appear on the graph, so I have to use algebraic methods. That's where this will come into play. So we're going to use what's called the polynomial factor theorem in order to use one root as a starting block to find the others. Now, just as a reminder, anytime we get a remainder of 0, that means we have a perfect factor. So if you get a remainder of 0, you know a factor of the polynomial. If you know the factor of a polynomial, then you know that it is an x-intercept. So if you have a factor, then you know there's an x-intercept there. And that kind of makes sense if you think about how we've been factoring and solving all the way back to quadratics. If I had something in factored form, and I'm just making up these values, if I had something written in factored form like this, if we set it equal to 0, we could go through factor by factor to solve for x. So this is nothing new. The only thing that's new is the fact that now we're able to apply this to higher degree polynomials. So let's see an example, and we'll go from there. All right, we want to find all of the zeros of the polynomial f of x equals 2x to the third plus 11x squared plus 18x plus 9. Given that x plus 3 is a factor of the function, so I know that I could rewrite this factored polynomial as x plus 3 times, this would be 2x squared, I know that much, and then stuff. I don't really know what's over here yet, but we can find that. Because if I know a factor, then I know that I've got a solution, or a 0 at -3. And if I know that, well, I can go ahead and use synthetic division to divide that out. So if I'm dividing out this factor, I can figure out what is left in these parentheses chunks here, and then maybe continue to factor or solve that. So let's go ahead and do that. I'm going to steal these coefficients. It doesn't look like there's any skipped terms, so we're going to steal those coefficients and do some synthetic division. Again, for this process, we're going to be going down, then diagonal, then down, then diagonal, then down, then diagonal. Every time we go straight down, we're going to add, and when we go diagonally, we are going to multiply by this number, in this case, -3. Now, if we do this correctly, we should get 0 as a remainder because they told me that this was a factor. So the fact that this is a factor means we know a solution. So if it's a solution, the y value would have to be 0 because it's an x-intercept. If I get something other than 0 there, I made a goof. We'll have to work backwards to find it. All right, so let's start this off. Drop down the first number, 2, and then we go diagonally, multiplying by -3, I get -6. Add straight down, I get 5. Multiply by -3 diagonally, I get -15. Add straight down, I get 3. Multiply by -3 diagonally, -9. Add straight down, hey, we got 0. Shazam. All right, so what I've just found is the stuff that would have gone in the parentheses here if I tried factoring that thing out. So if I really wanted to, I could write this in factored form as x plus 3. They gave me that. And then 2x squared plus 5x plus 3. So now that that's factored. Okay. Well, let's continue to factor, if we can, this bit right here. Let's see. I know it's going to have to start off with a 2x and a 1x. And I want to get a 3 at the end. So these numbers would have to be a 3 and a 1 because 3 is prime. And the end goal is to add to get a 5. Let's see. If I did 2 plus 3, that would give me 5. So to get a 2, I could put a 1 here. So then 2x times 1. And then 3 would go there, make them both positive. So I've got x plus 3 times 2x plus 3 times x plus 1. So my three solutions that I'm getting here are going to be x equals negative 3. We already knew that. X equals negative 3 halves. Remember the shortcut for this, take the opposite of the constant divided by that coefficient. And x equals negative 1. I've got three answers. This polynomial had a degree of 3, which tells me I should have expected 3. It's all checking out. All right, next one. Find all of the zeros of the following function, given that x minus 1 is a factor. Well, I know that one of my answers is going to be x equals 1. That's kind of a freebie. This thing is a cubic, which means I should have 3 total. I need to find the other 2. So just like before, we'll do synthetic division. I'm not seeing any skipped terms, so I don't need to throw any placeholders of 0 in there. And I'm preemptively going to throw a 0 down as my remainder, just as a little self-check for me, because they tell me it's a factor that should work out to be 0. Oh boy. All right, so let's start this off. Drop the top number straight down. Whenever we go diagonally, in this case, we're going to be multiplying by 1. So whenever we move diagonally, we're multiplying by 1. So we have a 2. This is a 2 here, then a 5. 5 here, negative 3, yay, 0. So now we're going to have x minus 1, that was given, and then we just found this factor of 2x squared plus 5x, plus 5x minus 3. Well, let's continue to factor if we can. Let's see, I'm noticing that this looks pretty similar to the last one, doesn't it? Yeah, the only difference now is it's a minus 3. Well, if it's a minus 3, that means I'm going to have, between the 3 and the 1 of them's got to be positive, one's got to be negative. So if I could get a 5x by maybe doing, a 3 times 2 to get a 6x, and then minus 1x, so plus 6x and a minus 1x, that ought to do it. So if I put a plus 3 here and a minus 1 here, that would give me a positive 6x and a minus 1x. So that ought to work. Okay. And then we still have the x minus 1 chilling out front. So our three solutions would be x equals 1, x equals 1/2, x equals negative 3. Next problem. Find all of the zeros given that x equals negative 3 is a 0 and x plus 1 is a factor. Now, they're giving us equivalent pieces of information here, but they're kind of speaking different languages. I'm noticing right off the gate, this is x to the 4th, so I'm going to expect 4 total answers, and they're really giving me 2 of them, so I just need to find the other 2. So they're giving me 2 to start, I need to find the other 2. When they tell me that x equals negative 3 is a 0, that's basically them telling me that x plus 3 is a factor. Those are equivalent statements. If x plus 1 is a factor, then x equals negative 1 would be a 0. So they're giving me 2 x-intercepts, 2 zeros, if you will, aka 2 factors as well, but they're just kind of expressing it in different formats. So what we can do is we can divide out each factor, because if I took away an x plus 3, if I factored that out, and then turned around and factored out an x plus 1, well, I'd be left with, let's see, there's an x here, so I would need 2 x's in here. I'd be left with something x squared, something x, and then some sort of constant. So basically what I'm going to do is I'm going to divide out one of these numbers, then I'm going to divide out the other one, and then go from there. So this is going to be kind of a two-step synthetic division. It's going to sound scary, but it's really not too shabs. And I'll try to color code this. So the first one, I'm going to start off by dividing out the -3. All right, there's no skipped terms, so I can just write the coefficients: 2, 7, -4, -27, -18, and I'm preemptively going to throw a 0 because they're telling me it was a factor. Sorry for the terrible penmanship. All right, let's get mathin'. We're going to start this off by dropping straight down with the 2. And when I go diagonally, I'm going to multiply by this number in the box, in this case, -3. So this would be a -6, add straight down to get 1. Multiply diagonally, I get -3, add straight down, -7. Multiply by -3 across, get a +21, add straight down, I get -6. Multiply diagonally, +18, add straight down, yay, we got a 0. All right, so this is what I'm left with. 2, 1, -7, -6. Well, here's what I get to do. I get to take these values that I just got and do synthetic division again, only now this time I'm going to use the other value that was given to start. So for this one, I'm going to use this -1 and throw that down here. So when we do this, same process. We'll add straight down. Whenever we multiply diagonally, we're going to multiply by the number in the starting box over here, in this case, -1. So add straight down, multiply diagonally, add straight down, multiply diagonally, and we already knew it was going to be 0. Now that we've got this thing whittled down, I've got my coefficients, so 2x squared minus 1x minus 6. Now some of you may be wondering what would happen if I flip-flopped these, maybe did -1 up here and a -3 down here. How would that change things, and which one's the correct way to do it? Doesn't matter. You can switch the order. It does not matter. The only thing that matters is that you're using the quotient of your first problem as the dividend of your second. All right? So if you just try to divide out, if you use these 1, 2, 3, 4, 5 values for both, you're going to get nowhere. So you want to whittle this down from 5 numbers, down to 4 numbers, down to 3 numbers, and then we can factor it. Okay. So we've got to factor. I've got 2x squared minus 1x minus 6. Let's see if we can factor that. I know it's going to start off with a 2x and a 1x. And then I know that these numbers here have to be factors of 6, right? I can use a little bit of knowledge of GCF. There's no GCF here, which means no even numbers are allowed in here. So if I used 1 and 6 as my combination, well, 6 can't go here. It would have to go here. But if I did 2 times 6, I'm going to get a 12x. That's way too big. So it's not going to be 2 and 6. Or sorry, 1 and 6. So that means it's probably going to be 2 and 3. Well, 2 can't go by the other 2. That would create a GCF, so I'll throw a 2 and a 3 in this format. And let's check out the middle term. It's got to equal out to be a -1. So I've got a 3x and a 4x. If the 4x was negative, that would work out. So 3x minus 4x would give me that -1. All right, so now let's get our answers. So we should have 4 solutions total. They gave me 2 of them to start. So I've got -3 and -1. Those are 2 of my answers right out the gate. And I just found the other 2 factors, so I know the other 2 answers. So my 4 answers would be x equals -3, that was given. X equals -1, that was given. X equals, we'd have -3 halves. We just found that. And x equals 2. Those are the 4 solutions. All right, getting warmer. Example 4, find all of the zeros. Given the function, ooh, I'm noticing, hey, we got a skipped term on this guy. We need to have a little plus 0 at the end. Remember, whenever we're doing these, you always have to go in descending order, highest exponent down to the constant. And they're giving me two values. So I've got x equals 0 is an x-intercept. So that'd be the origin. And then x minus 1 is a factor, which is another way of saying x equals 1 is an x-intercept. So we'll divide out one then the other. The order doesn't matter. I'll do the 0 first, then the 1. But again, it does not matter. So let's get started here. So we'll have 0 in the starting box, then we'll throw our coefficients, 1, -5, 3, 1, 0. Now, since 0's in our starting box, you can better believe we're going to see a whole bunch of zeros going across, because when we multiply diagonally, we're multiplying by 0, and as you know, anything multiplied by 0 is just 0. So this one's going to be kind of a gimme. Now, if you think about it, this kind of makes sense that we'd be left with these same exact coefficients, because essentially all we did was just factored out a GCF of x out of all these terms, right? So after we factored that out, you get 1x to the third minus 5x squared plus 3x plus 1, which is exactly what's right there. All right, so now let's factor out or divide out the 1. So again, I'm not going to pay any mind to the remainder. So we knew the remainder was going to be 0, so I'll just pretend that that's not even there. We're going to do synthetic division again. So I'll drop down the first coefficient, then multiply diagonally. In this case, I'm multiplying by 1. So I'll have 1, and then here's a -4. Multiply diagonally, get -4. Add straight down, multiply, add, boom. So now I'm getting x squared minus 4x minus 1. Now, I want to find all of the zeros. I should have 4 total. They gave me 2 to start. That means the other 2 are buried within here. Normally, I would try to factor this. But if I try to factor, there's no numbers that multiply to be 1 and add up to -4. So these are not going to be clean, pretty numbers. They're not going to be rational. There's a chance they might be real solutions. There's a chance they might be imaginary. We're going to have to find out. So what I'm going to do is I'm going to set this thing equal to 0 to figure out the roots. Now, I have 2 options. I can either do completing the square, which is probably where I'm leaning, or I could do quadratic formula. Both are equally valid. All right, so I'm going to do completing the square, which means the 1's got to go to the other side. And I'll leave a little blank space. Then I got to figure out what number could go in this blank space to create a perfect square trinomial. So to do that, I take half of 4, which is 2, and then square it, which is a +4. So from here, I'll write this left side in factored form, which would be x minus 2 times another x minus 2, or x minus 2 squared, and that's equal to 5. Square root each side. X minus 2 equals positive or negative rad 5. And we'll move the 2 over. So x equals 2 plus or minus square root of 5. That is 2 answers combined into 1. That plus or minus tells me there are 2 answers total. So my 4 solutions that I've found. Let me steal this because I'm too lazy and I don't want to rewrite it. We've got x equals 2 plus or minus rad 5. And then the stuff they gave us right at the start, x equals 1 and x equals 0. And there we have our 4 total answers. All right, last and final one, and then we are done. We want to find all of the factors of this polynomial, so 4 total, and they're giving us a factor. Ooh, and it's got a multiplicity of 2. So what that means is that we've got a 0 at x equals 2, but graphically it would kind of be a bounce point because it's got an even multiplicity. But what I get to do is I get to divide that thing out twice when I do my synthetic division. So I'm going to have 2 in the little starting block, and we'll do our synthetic division, and then I'm going to do it again with 2 as my starting number. So that's what the multiplicity of 2 means. Let's get our coefficients. Oop, got a missed term right here for x to the third. Make sure you're keeping a Hawkeye out there. So 0x to the third. I need to throw a 0 in there. So we'll have 1, 0, -6, -8, 24. And I should expect to see a 0 down there. All right, we're going to drop our first number down. Whenever we go diagonally, we are going to multiply by the outside number, in this case, 2. So add straight down, multiply diagonally. Add straight down, multiply diagonally. Add straight down, multiply diagonally, and lo and behold, we got 0. All right, now we're going to do synthetic division again. Since it had a multiplicity of 2, I get to do it 2 times. And since there's a remainder of 0, we can kind of disregard that for the synthetic division process. So we're going to add straight down, get a 1, multiply by 2 going across, add straight down, multiply by 2, add straight down, multiply by 2, and hey, we got a 0. Neat. So now my quadratic that I have left is going to be 1x squared plus 4x plus 6. I need to factor that out. X, ooh, that is gross. X squared, my bad, plus 4x plus 6 equals 0. If we can, we'll factor it. If not, we're stuck with completing the square quadratic formula. There's no numbers that multiply to be 6, but add up to 4. Dang it. All right. You know me, completing the square, big fan. You could do quadratic formula if you want. Either one's equally valid. So completing the square, I'll kick the 6 to the other side. I need to fill in this blank to make it a perfect square trinomial. So take half of this b value and square it. Half of 4 is 2. 2 squared is positive 4. So I'm going to add 4 to each side. Then I'll write the left side in factored form, which would be x plus 2, quantity squared, equals -6 plus 4 gives me -2. Now when I square root each side to get rid of that radical, right here I've got a negative trapped underneath the radical, so I'm envisioning imaginary roots to show up. Bum, bum, bum. So we're going to have x plus 2 equals, we took the square root, so I got to have a plus or minus there, I rad 2. And again, that I is just to indicate there's a negative underneath the radical. I'll subtract the 2 over. So you get x equals -2 plus or minus I rad 2. So this counts as 2 separate answers, right? The plus or minus count as 2 separate answers. And then my other solutions were x equals 2, and then x equals 2 again, because it had a double multiplicity. It had a multiplicity of 2. So right there, folks, we've got our 4 total answers. This was a 4th degree polynomial. 4 answers should have been expected. All right, that's it. That's all. You know the drill. If you have any questions, please let me know. And as always, folks, good luck. Have fun. Be safe. Roll Tide.